if you're in traffic engineering. So certainly it's the area under the curve. In this example, of course, the force was constant and the displacement was linear. And that's kind of the simplest kind of mechanical energy or work that you can have, as a matter of fact. The second region is similar to a varying force of a spring, and that's an ideal spring, means no internal friction between the coils, and it was initially compressed with respect to the reference position X sub O, which means it was moved back toward the origin and then released, and it then began to elongate, having some velocity as it goes through its rest position. Now it continues to become elongated by as much as it was compressed. Ideal springs. And of course the first half was a compression, which is positive work because it's above the axis, and the elongation was below the axis, and that is a negative work because F sub 4 is now a minus. So if I were to add the areas under these two triangle curves, 1/2 base times the height, base is the change in X, height is F, we would find that in each half cycle, in other words, moving from a compression to elongation, which is the bottom of oscillating springs, the net amount of work is 0 for an ideal spring, of course. If you're having some difficulty picturing ideal springs and what happens to them, I believe I mentioned that there are some frames in Chapter 15, and it's intermeshed there between Chapter 7 and 8, but we're not going to be studying and analyzing spring transfer of energy, which is simple harmonic motion, until the end of the course. And so I'll just throw out that in Chapters 15, PowerPoint presentation, which is an earlier presentation than the 10th edition, I'm only interested in pages 1 through 10. It will help justify the variables that are going to be used today and sort of gives you an example or an explanation of what those variables are, which I believe includes the first 3 sections of Chapter 15, 15.1 through, I believe it's point 3. I'll research that, but I believe it is the first 3 sections. And if it looks like it's beginning to introduce variables that we haven't encountered yet, like the acceleration along this motion, the acceleration of the hanging mass from the spring, or the elongated on a horizontal surface, is not constant. Why do I know the acceleration in region B is not constant? Ladies and gentlemen, somebody got a good explanation? Or what is this graph saying? The acceleration along region B at no time has the same value. It is always different from point X sub 2 down to point X sub 3. Uh-oh. Can I use Newton's second law here? Can I use the kinematic equations for region B? Uh-oh. I need somebody to respond here. We don't have time to go all the way back to Chapter 2 and Chapter 5. Somebody needs to know this. Is anybody still here?
You are now unmuted.
Uh-oh.
I'm still here. I'm trying to figure out your question, though. I'm confused on
All
how
right,
you-
look at look at region B, which goes from X sub 2 to X sub 3. The diagram has skewed X sub 3 a little bit, but it's the vertical mark in the grid. What that line tells you is the force is changing constantly from a plus 4 f sub 4 to a minus x minus f sub 4.
And what is your question?
What does that line tell you? Well, first of all, the force is
acceleration, or?
All right, first of all, it tells you that the force is changing consistently. There's no two values on it. No, the slope is constant there. But looking at that graph tells you that when you go from f sub 4 down to f sub minus 4, there is no 2 points on that distance that has the same force value. And it doesn't have the same x value either. So the force is changing from positive f sub 4 to minus f sub 4. And if the force is continuously changing, well, whatever mass is hanging, that's not going to change. Well, it must be changing. Folks, you're expected to know the content we've studied so far. And we've studied Newton's second law. Can someone verbalize Newton's second law? What is the equation for Newton's second law?
You are now muted.
Absolutely, and if the mass is constant, and if the force is varying continuously, what can you conclude about the acceleration of this system in region B?
You are now unmuted.
The acceleration is not constant.
You are now muted.
You're right. This is how you have to learn how to apply the knowledge you should already have, ladies and gentlemen. And if we went back and looked at work is F dotted into the displacement, if the displacement is changing and the force is changing, we've got a double integral. I don't know if any of you are already in Calculus 3. So one way to get around that, because this book confines integrals to just one integral, we may want to take areas under curves then until we develop a little bit more mathematics, folks. So that's one reason why I approach this lesson using the graphic method. And there's some of this applied in your homework, ladies and gentlemen. Okay. That's why we know that we have to deal with this without using the kinematic equation. Okay, here we go. Got through that. All right. In region B, springs and simple oscillators are studied in greater detail in later chapters, and I mentioned chapter 15. But if you do not know Hooke's law, I need to talk a little bit about what's happening. Now, this should say F sub R, which means the resistive force of the spring when it's either compressed or elongated. And even if I look at the compression as being X and the elongation being X, I know that the elongation has a negative value and the compression had a positive. So they're still not the same value. The same magnitude, yes, but not the same value of force because there's a direction associated with it. We find that if in the 8th grade or something you had a spring and you elongated it and they had you measure its elongation, why a certain mass or its equivalent weight is hanging, you really established the Hooke's law, which is defined, well, it's not defined, it's empirically derived as being negative, which means the spring is pulling back on that compression, actually it's pushing, or it's pulling back on the elongation. This equation is discussed more at length in chapter 15. So if you're having a little difficulty understanding how this can happen, please, there is one homework problem associated with this lesson in chapter 15. I forgot what the number is, 1 or 3 or something. You may want to make sure you look at that problem. The equation for Hooke's law is minus K which is the elastic constant, sometimes referred to as the spring constant, sometimes referred to the elasticity of the spring. It is still just a spring constant, K, and every spring has a different spring constant. It really comes out of its cross-sectional area, what the loops are made out of, how many loops per length, how thick the material is that forms the spiral spring. Obviously, the shock absorbers, and with their springs, are going to be pounds and pounds before it's going to compress very much. The springs on a train, if you've ever seen them, huge. Some of them are as thick as a child's arm or something, looped around there. So K is a characteristic property of how the springs are made, what they're made out of. It really represents the storing force of the spring's coils. In other words, what they're going to either push back or pull, and is proportional to the spring's displacement. It acts to oppose the direction of the compression or elongation, but the spring only interprets it as a constant value. It doesn't know up from down or left to right. This last statement makes sense as the spring tries to restore itself to its equilibrium position at all times. I have illustrated some of the discussion in Chapter 15, hopefully to kind of get you to realize what's happening here. To the far left here, I have 4 loops of a spring that I have placed a mass on. If this spring were not elongated, in other words, if I had a platform that I put the mass on, let me just kind of pull this in here a little bit like this. Come on. Oh, let me get my writing tools in order here. In other words, if this last loop had an extension like this right here, whoops, and it would be then in its so-called rest position. Then I add all of this mass here. And with that then, I would have, you pull it back the other side. Oh, here we go. Whoops. Give me a minute, folks. Here we go. Got it. And I'll push and drag. I'll do it this way. Whoops. Well, this is what I'm going to do. I'm going to go back this way, get rid of that, and then go this way. Well, can't get it back. Well, what happened when I place this, I allow it to come to its new rest position right here. Now, this is the rest position when it has a load on it, right in here. I've got too small a. Here we go. Got that. I don't really need to see it anymore because that's my reference position. Oh, come on, folks. Come on. Oh, I'll use the underline. So this really begins the problem when I have a mass hanging without a mass on the spring. I just have a spring. So when it was just sitting there uncoiled, not compressed in any way, had a little platform there that I put a mass on, and then I got out of the system. I didn't want to be part of the system. I don't know if any of you had a chance to begin to read Chapter 8, but they talk about systems inside and outside of the system, and it gets a little annoying, but bear with them. They're trying to make a point, and I have an equation that we'll be developing that will make things a little bit easier, I think. But once the mass is on the spring, it's elongated to a new rest position, and they sometimes refer to this as the X sub O position, and as a mass spring system isolated from anybody, it would then be called its rest position or its no motion position. Now, if we did not interact with this mass hanging from the spring now, it would never begin to oscillate. For that reason, and I don't know why I can't scroll this back down. I'll see if I can get, oops, here. See if I can get it down or up. I tell you what, let me get out of this and then try to reload it. Because I'd like to write on this first lesson. So give me about 3 minutes or so, ladies and gentlemen. Oh. Yeah, here we go. Don't know what happened, but it happened. It happened to me once when I was doing this in May. And, well, I don't know what happened to it there. Ladies and gentlemen, I think I'm just going to get out of this and go ahead and go to the lesson. I'll only be able to hear you, or if somebody on the earphones wants to type something, and if one of you that are on sound, if you'll read it to me if they have a question. Do I have anybody to kind of recognize that? Anybody want to say that they'll read me whatever somebody says, writes, types?
I can try and keep up with it, but if I have the PowerPoint pulled up, then I'm not going to be able to read what they're typing at the same time.
I know. Well, let me see what happens on the second frame, but, well, it chops it off too. Let me try something else. Okay, here we go. I'm going to start by clearing the field. All right, go to a whiteboard, which means it resets the whiteboard. That may have done it. Nope. Well, I'll try going a little bit further. The illustration that I was using with respect to the spring, oh, now it's really messed up. Ladies and gentlemen, technical problems. I'm going to go ahead and exit conference, and I'll come back when I move to, although I was going to, once I get into the PowerPoint lessons, I can move smoothly from one to the other. I just can't write on it. I'll keep coming back and see if anybody has any questions. Our next lesson, if you have questions about Chapter 15, is what I'm trying to cover here. So let me go ahead and I'm going to move to the lessons in the home page. And if you'll also do the same thing, everybody that needs to, unless you have made a copy of these PowerPoints, which I don't require, but you may want to make a copy. I don't mind. It's I wrote them, and therefore anybody that wants to use them to augment, excuse me, to augment. Ooh. Their learning. In fact, I've even recommended Khan Academy has some good presentations, ladies and gentlemen, that, let's see, here we are. Okay, I'm just going to go to full screen and end up with our fifth frame. If any of you have not gotten to it, you might want to say we're going to go to the fifth frame, where once I have placed the mass on the spring and lower it gently to its rest position, and this is the working rest position. It is, if it's an ideal spring, it will be lowered by an amount that will limit the compression which means if you allow it to oscillate freely, it will not displace itself more than the distance that it was just lowered to. That's why it's identified as the rest position. In order for this spring to begin to work, we're going to have to come out of the spring system back into the spring system, and we want to manually elongate it and release it, or manually compress it and release it, and its oscillation or vibration will begin to occur on its own. And of course, then I get out of the system. There's only one problem with that compression and elongation. It is limited. It's bounded. The compression and the elongation should never be greater than the change in height when I added the mass and it came to a new rest position. In my diagram, I call that positive Y, capital Y, and it will vibrate then by that same Y amount or a fraction thereof. But you cannot compress a spring any more than that because you're adding more energy than the spring can manage. And we'll see the energy equation depends on that K value and the elongation. It is also showing the type of oscillation. As soon as I pull the mass down, that's a quarter of an elongation, which we call the amplitude at that point. If I release it, it goes back up to the rest position, so it's gone through 2 amplitudes. Then it goes back up by the same amount, and it hits the place where it looks like I originally placed the mass. Another way to get it to oscillate there is to gently place the mass on it and let it begin to oscillate. Don't throw it. Don't give it any energy of motion. Just place it on the platform of the spring and let it begin to oscillate through its what we call amplitudes, which is its maximum possible displacement. It would have to come back another quarter cycle, which would be 4 amplitudes. Now, the reason I mention these displacements is I don't know if any of you have accessed a study guide to this book, which has many typographical errors. They quit publishing it, so you may have one that has references to other editions. One of the major mistakes that they made in that student study guide was they said that a spring only has 2 amplitudes. Ladies and gentlemen, that's wrong. Amplitudes are measured from the rest position to the elongation of a quarter cycle. Just that definition tells you you must have 4 amplitudes to complete a cycle. So that kind of makes sense just by the way it's defined. And of course, a spring always tries to restore itself to its original rest position, which on the graph of frame 6 is really the excibo position. And from that frame, I think you can see where the area under the curve in region 1 is the same area as in region 2. And as I mentioned beforehand, any area under a graph that you have constructed properly with an origin at 0, 0, 0, or 0, 0, we're just doing planes, not 3 dimensions. These energies cancel, which sort of implies that the spring had energy that was positive and it used it up in order to complete a cycle because it's trying to get back to the rest position. The area under the curve from x2 to 0 is certainly in region B1, you might say, and the height is f sub 4. The length or base of that triangle is 1/2 excibo minus x sub 2, and I think you can see that that is the area of the triangle. And if you took the area of the triangle in region 2, F would have a minus sign, so the area under the curve certainly represents whether or not it's gained or lost. So just watch your minus signs. They become a little important when interpreting graphic material. Okay. The third region, which is out of our realm of study, but in order to prepare you for maybe analytical mechanics, for those of you becoming mechanical engineers, what you're left to use here is actually something similar to the Simpson rule, the trapezoidal rule, and I believe it's your calculus 2, and might incorporate some of the theory when you get to your applied differential equations. But let's just look at it with respect to the dot product. And here's where the dot product becomes extremely significant. The work under this curve in region C from your x of 3 to the x of 4, which is covered by the curve itself, would be the integral notation from x of 2 to x of 3 of the force. And it may be a Hooke's law with a spring that is not ideal. So I kind of mentioned that it could be Hooke's law that we're trying to find for an irregular shaped spring. One maybe has a larger diameter of the coils at the top as opposed to the bottom, or vice versa. And notice that it is a dot product, but we have a change then in position. Well, we would have a change in value for F if it were a Hooke's law type of change. There's something wrong here with this integral. This integral says that I have a direction for force and I have a direction for x. Yes, both of them are vectors. And when I take the dot product, do I get a vector or do I get a scalar quantity? Think back to your quiz today.
You get a scalar quantity?
Absolutely. They have defined the work as an integral so that it would be a dot product, so that you get a scalar quantity out of it. And why do I emphasize scalar? Because remember I said work is from one place to another. And you could have gone to the moon between those two positions and come back and you'd never know it. This integral could have been all kinds of loops and everything, to the left, to the right, top and bottom, between f of 3 and x of 4, and yet it ends up at that final position at x of 4. So determining work sometimes doesn't tell you everything you want to know between the 2 points. However, if you just wanted to know if it went in a parabolic path of some kind, of course you'd have to know what this function is. A array around this difficulty is to perform the dot product, thus producing a scalar product in the integral. And then go to the next slide. That's easy to follow. Work. But we said that this probably obeys some kind of Hooke's law, as irregular shaped as a spring might be. You could still add mass. Yes? It's 8. 8. Oh, okay, 8. Okay. Oh, well, come to think of it, I was talking about region 3 over here. In fact, you can use this same work integral for the regions between 2 and 3. I see what you mean. What I did is I said, since this function, the integral from some initial to some final x, could be used for any one of these 3 regions, and I was led to that by looking at region C, but I really want to go back and apply it to Hooke, because I know Hooke's law for an ideal spring is minus kx. And I know that the x is going to change, and that will enable me to integrate this function, ladies and gentlemen, if you think about it a minute. Okay, here we go. And it says work done by spring in the first half cycle. And notice that that would be F dot, and the F should be inside the integral, incidentally. Work done by the spring is going to be if its compression is trying to move it back to the origin, which is in the opposite direction. So the dot product yields a cosine of 180 degrees. This is extremely important, folks. to know that there's a -1 there. The restoring force of a spring is the tendency of the spring to return to the rest position. And if you've compressed it upward, it's going to tend to move down. If you elongate it down, it's going to try to move up. Using Hooke's law for the force, notice that I place the kx value for the magnitude, because remember, when you took F dotted into dx, you wanted to look at that force acting, in this case, 180 degrees. I would then get the integral between the two bounded conditions. If you wanted to call the rest position 0, this would be a -x to a +x then. Your x of 2 became a -x with respect to the rest position. At the compression, it would be x. So 3, or elongation x of 3. X of 2 is compression. Well, I have this going from elongation to compression, which is going to give the same value anyway. Spring doesn't know up and down. With x measured from the rest position, of course. The work done for half cycle then is integrate, take the -k out because it's not varying. It is the elasticity, a constant. And the integral of x dx, would everybody agree it's x squared divided by 2? Integrate x dx, folks. What do you get?
Yeah.
Yes, you do. And here I have it going from the elongation, which is -x, to the compression x. What work done by an ideal spring, once you leave it alone to let it do its oscillation for a half cycle, would be to place the final x in here, which I have done, and the initial, and notice that I've kept parentheses around the -x, and realize now that I've got -k, x squared minus x squared divided by 2, and of course that gives you 0. So once the spring begins to move, and you know you had to put energy into it, remember, you had to compress it or elongate it without giving it additional energy, it's going to try to continue to go back to its rest position. As it goes through its rest position, it will have velocity. It will not have acceleration. For those of you that have studied springs and know a little bit more about what's in Chapter 15, will realize that that is absolutely true. In fact, they were talking about the integral here is exactly what determines, of course, the area under that curve. The kx squared really looks like a 1/2 of a base times a height type of calculation. That the graph represents oscillation of an ideal spring and no friction between the coils. I've sort of said that a few times because it's critical in these equations. Now, concentrating on C, since we know that integral notation will give us an answer, in the case of Hooke's law, we know that equation for force was -kx. We would need to know the equation of motion for region C, just using the same technique of an ever-changing acceleration ideal spring. Excuse me. We could graph the data here if as an engineer, excuse me, if as an engineer you're having a little bit of trouble determining points on something that is moving like this, you might call in a mathematician or a physical mathematician. And usually every state university that is funded by state funds will have someone that will be glad to help you find this curve. The University of Florida has been doing something like this since 1853. So they're pretty much familiar with their obligation to commerce and industry and areas because they had state grants, land grants. They're financed in the state retirement system, as I am, and get paid real good, too. how can we find that function? Well, ladies and gentlemen, let's just know that we were given the function somehow. Unless you're a mathematical physicist or maybe a theoretical physicist, you might not be able to come up with that. But there is some way of accessing. Every state has a state university, at least one. Colorado, I think, only has two, and it has a private one. But so we're going to kind of know that we can know the function. I tried to make this look very much like a parabola. The intention was that it would be. And then a close approximation of the function was f equals minus f sub 4 plus x squared times f sub 4 divided by, now this is the second term that is being divided by 12.96. And notice I went to 4 significant figures just so I could round off the 3, ladies and gentlemen. You need not write more than 4 in your homework or on test to get the point, because a lot of you found that I only use 2 significant figures in testing. Obviously 0.9, even if you got a 0.5, it would be rounded up to, say, 13. And if f sub 4, now notice I didn't have a value on my graph, if it was 12.96, then this equation would become minus 12.96 plus x squared, and the unit would be a Newton. And the work done is, and now I want to go to my integral notation. In the interest of space, I did not write the general equation, but if you had it at the top of the page, that's fine. We know that's going to be a work dotted into dx. So we have the work. I'm going to start from, I'm going to shift my graph down to, it's as if I took a Cartesian coordinate origin and shifted it down to a minus f sub 4. Notice then the integral would go from minus 12.96, which means it was shifted down to that point, as a binomial plus x squared, close parentheses dx. Now, notice carefully I do not have the dot product in this. And it's because I knew the graph was curved upward. Would everybody agree? If you want to put the dot product, notice that the expression is in x, and the differentiation is in x. This is like an I dotted into an I. What was the cosine of the angle when you have I dotted into I, ladies and gentlemen? Absolutely. Thank you for the review. I appreciate it. Okay. With that in mind, I have integrated it, obviously, minus 12.96x plus x cubed divided by 3. And I hope I don't have to explain why that was done the way it is. This is one of the skills you should have brought with you to the course, ladies and gentlemen. And notice that I suppressed, or I took units out, because you cannot integrate a Newton. You cannot integrate a meter. Here's where the I guess the science of work kind of falls apart. We know it's going to be a Newton times a meter, and I kind of estimated along the x-axis some value, 3.6 meters, 1, 2, 3. It's just a reference point. Substituting those values, I find that the work is negative 31.1 joules, or Newton times a meter. Does that make sense, everybody? Now, I know over half of you have earphones, so I hope that it makes sense to you that the work being done, whatever's causing it, it has done more negative work than positive. If you use the trapezoidal rule or the Simpson's rule to find the area under this curve, where I've identified x above as 0 meters to some final value in the above the graph, or above the x equals x in meters. Does everyone see where there is more negative work done here than positive? Does anybody just want to give me a yes on that?
I see what you're talking about.
Yeah, it's a lot of area down there in the negative. Now, why am I keep mentioning negative? Ladies and gentlemen, during a test, when you're taking area under the curve, sometimes you forget to use the negative. Believe me, I've been teaching so long, I know about what's going to happen. And I should have mentioned when we talked about the vertical circle in Chapter 6, the equation that we had, tension minus mg cosine of the angle equals the centripetal force. Ladies and gentlemen, I bet you when that's on your next test, oops, I just gave it away, that a third of the class is going to miss it because they're not paying attention to the angle. They're just going to substitute values. Be careful. The vertical circle equation that I just quoted can be misleading if you don't use a diagram and take your time applying the equation. Same thing happens here. If you just take the area under the curve and forget to put a minus sign by the area below the abscissa here. Now, I want to try something. You notice that I have blocks, or I have a graph grid on this page. Well, I have it on a lot of pages. Let's count the blocks. Let's do that. Let's just see if the area under the curve matches to at least 2 significant figures, I'm hoping. 1, certainly. So let's begin to count blocks.
What number are you on?
I'm on frame 11 now.
Thank you.
Thank you for that. Yeah. And notice that I have cordoned off a block. And I've sort of given a value here. And then I want you to count blocks. I go 1, 2, 3, 4, 5, 6. A little more than 7. And then the block below it, and the block below it. And I count about 20 blocks or portions thereof. The area of the curve then, actually I think it's something like about 20 and a half blocks, but that's okay. 20 blocks times a minus 1.6 Newton meters, which I got from the area of my, you might say, identified unit block. And I think you'll find that that area was minus 32 Newton meters. It depends on how you do a rough approximation of blocks, including the ones above the x-axis, which were positive, along with the negative. So you can use area under the curve, and I never, if you've noticed on my test, I never put selections close to one another. So if you got an answer of minus 32 Newton meters counting 20 blocks and the unit square, I think I would have had maybe a selection like minus 31, positive 31, minus maybe 28, but I'm not going to have an answer of minus 32. It's too close to the true answer. So if your integral notation is beginning to fail you a little bit, you might want to go to just look off a unit block and find out how many are under the curve, minus how many above the curve, positive. So there's really 2 ways of doing that, ladies and gentlemen. Not a problem with it. And of course, that last calculation was a rough approximation. Well, actually, my function was a rough approximation. I even tried to get it so close with the 4 significant figures. But it also serves to illustrate that as you were taught integral calculus, it was really determining the area under the function that you were using while you were learning the calculus. Some of you might remember that. I would like to do an example of what we mean by work done against the inertia of a mass. This is tricky. Well, I can look at that. It looks like I'm pushing a mass like we did when we were in Chapter 5 and like we had a test problem on our last test, although it's been covered up with some of the writing. But if you look to the diagram right in the middle of the grid, you see I have a force applied at an angle A, and I am only interested in the horizontal component since I know the surface is rigid enough to keep it moving horizontally. That is an assumption, more than an assumption. We know that will be true, that the table has enough elasticity of pushback So the normal force will support the portion of the weight needed, or add more because I'm pushing down. And that's similar also to how the normal force would change if the applied force was at an angle. So I know that I have a net force, F times the cosine of the angle, which is parallel to the direction of displacement. And I notice that I have an initial and a final X. And now, anytime I draw a diagram of work, usually you will have one initial, which would be a position initial, X sub I. Now, because of the situation of the I's and F's subscripts being a little confusing, in fact, your book starts using, let's say, X sub 0 instead of X sub I. Ladies and gentlemen, if when you establish your 0th position in work problems as being the initial, you may want to label it 0 or X sub 0. You're telling me where you're going to establish a measurement of 0. And everybody independently can assign that. Everybody could have a different one. And X final then would be the only lettered subscript. We will allow this mass to start from rest and know that the velocity at position final is not 0, and it's still moving. In other words, if I've been applying this force, I've had to run along with this block to continually supply this force, and I know then it's going to accelerate. Would everybody agree? I'm back in a situation where acceleration is constant. Okay, work done on the mass to overcome its state of motion, inertia, which means the first law. So we're back into constant acceleration. We know the system is inertial then, and it obeys the first and third laws, actually. Notice I use the applied force equation, F dot dx. Ladies and gentlemen, have you ever wondered why the equation for kinetic energy equals 1/2 mv squared? When you took maybe physical science and middle school, or some of your algebra in high school had equations 1/2 mv squared, and they told you that was a measure of the kinetic energy of a mass that had a velocity v. That equation came out of calculus on work being done against the inertia of the mass. In other words, work being done to get the mass to start moving, as someone quoted that first law in the answer to that last quiz. That was good. I like the quote, but it's the first and third law. Notice that I have removed the dot product because, again, the red force vector is all that I'm interested in, and it was F times the cosine of A times its direction dx. Well, I can't fix that. Oops, there we go. I know that the net force is going to be the mass times the acceleration in the x direction, because I know the acceleration is constant. Then I know that mass is constant. I'll take it out of the integral notation and realize the acceleration, which is constant, so I can move to the instantaneous first derivative of displacement with respect to time, and then the second derivative, which is dv sub x divided by dt. This becomes integratable. The second line says v sub x dv sub x. Well, I thought this would be 1/2 mv squared, going from v sub o to v final, placing those values in my answer after integration between those bounded velocities. I find that I have 1/2 m v final squared minus v initial squared. If v sub initial were 0, and it was, then the kinetic energy of this system is now 1/2 m v final squared. At that instant in time, I can continue to add energy by continuing to push it. Okay, here we go. Okay. Work done against the inertia of a mass. The expression down here for 1/2 mv squared is defined to be the kinetic energy equation. Thus, when any work is done on a mass, we can look at how its kinetic energy changed, and that would just be work. It's not change in work, it's just plain work. And that occurs also in electrodynamics, incidentally, and in physics too. Okay, here we go. I'm sure some of you may have wondered why kinetic energy was defined as 1/2 mv squared, and it was just illustrated to you why that happened. Okay. Now, work done against the inertia of a mass can lead to evidence that another force acts on a system. If you push a mass m across a surface, now here's what changes. The mass's velocity does not change. Uh-oh. We just said we know work was 1/2 mv squared. And if the velocity's not changing, and I've been pressing with a force, and it's still moving, ladies and gentlemen, I'm doing work on something. That's the definition of physics. And, of course, I'm wondering now if the surface may be rough. Would everybody agree? Well, let's do an example. Let's put some numbers in here. Oh, yes, we got a technical problem here. Work done on the mass. All right, it's 1/2 mv final squared, open parentheses, minus v initial squared, close parentheses. But wait a minute. The velocity was the same. So we end up with 1 kilogram times 25 meters squared over second squared minus 25 meters squared over second squared, 0. The math here tells us that no work is done on this mass. What? A force is applied, and it has a component in the direction of observed motion, but no work? Is this last statement incorrect? Well, technically, we have to add something to it. The work done against the mass's inertia is 0, but I did some work. I was sitting there pushing with that force at an angle. It did have a direction, and it did have a component in the direction of motion. No work was done on the mass, but on what is the work being done? Now, I gave you a hint. The surface was rough. That word was used in your first test to imply what, ladies and gentlemen? Yes, and here's where mankind only introduced the concept of friction, I guess, about, let's see, the advent of the Industrial Revolution, maybe 200 years to 50 years ago. They knew, like Joule did, that when you were boring a cannon, a lot of heat was produced. And we associate heat with friction. Just rub two hands together in the wintertime, and you feel that rubbing one surface over the other produces heat, the friction between even your hands. In other words, there's another force going on here, and it's hidden unless you get the surfaces at a slightly higher temperature and you get thermal energy as manifestation of mechanical energy, or the word for mechanical energy here is work. Yes, and we're going to modify then our diagram. And notice that when you're working with work and energy and mechanical energy, you do not use a free body diagram because it's a scalar quantity. We're using vectors here to show that the horizontal component of the force must be equal to friction, since the work done on the mass is 0, which means the work that I'm doing against friction must be the negative of the work I was doing before, because it would come to 0. This force, of course, is friction. Now, I want to stop for a minute. Ladies and gentlemen, when you use a small f, and that's not final, you're using it for force. You're really telling people that you're dealing with friction. That is the methods of science. If you're dealing with any other force but friction, use a capital F, like I've been using. If you use a small f and you mean an applied force, you're going to get it wrong, folks. And notice that I have the work done by the force. I know that the if it moves 2 meters, I'll have the force times the cosine of the angle times 2 meters. I put the 2 in front of the f, though. So gathered all the coefficients and put the unit to my far right. Excuse me. Water should have done it. Okay. The work done by friction, and notice I have changed the symbol for force. The angle now between friction to the left and displacement to the right is now what angle, ladies and gentlemen? Okay, just read it. They oppose one another. They're anti-parallel to one another. So they would have a value of, no. I'm glad you said it, because you'd be surprised how many students say 0. If you have one force acting to the left and another acting to the right, what is the angle between those two forces? They're not in the same direction. If they were the same, yeah, 180 degrees. And this is where students fail to realize that. And remember, I said we have a little sign problem here with work. We have to be a little more careful. So I evaluate the cosine of 180 being negative, the frictional force times the 2 meters. So I get a value for the work done by friction, because it was acting to the left, as minus 2, the force of friction times meter. And here's where I have a symbol next to a unit. And the unit always is the last letter or symbol that you have in an answer. Now, if I were to sum 2f cosine of a m and minus 2 little f m, I would sum to 0. Would everybody agree? If I'm looking at the work done by friction, and if I look at the work actually done by me, I end up with a value of 0, which means I was only doing work against friction. I never did work on that mass, because if I did, it would be accelerating. Remember Newton's second law. A lot of work that you do, once you get it started, that would be an initial velocity. You don't necessarily want to accelerate it, because you'd have to apply that force constantly. So you want to be very careful. If you want something to slow down, quit pushing it. Friction is the only thing that then acts on it. Okay, here we go. Now I've already added those two values, and then we get back to 0 for the total amount of work done on the system. A little bit of talk there. This is talking really about the net work done on the system in referring to region B on the previous graphing analysis as an example of this last statement. When a spring goes through a half cycle, the net amount of work it has done on itself is 0. And that was the area under the curve above and below the reference abscissa or x-axis. So this manifests itself as a spring doing work on itself based on its elasticity. The last example was mass not accelerating, was a system which included a friction acting from outside the mass system. And that, of course, was an example of an isolated system. The mass hanging in the spring, and all closed systems, energy is conserved. In other words, the spring is a closed system, isolated. It can usually is hung vertically so that its weight is provided with the force of elongation. An example of that. Just a brief discussion before I get into some examples today. Your book uses the symbol H for energy and how it will transfer across a system's boundary. I believe in chemistry they use H for about the same thing. I can't remember. I know it's not entropy. I think that's F. But if you plan to be a chemical engineer, you'll probably get that resolved. If I were to sum all of the energies in a system of, say, just sigma H sub I, when I goes from one end, H can be heat transfer in and out of a system, endothermic, exothermic. Mechanical work could be a push or a pull, or the work you can do on the mass. Energy could be mechanical wave energy, like sound or vibration. We're not going to deal with those. That is, remember the course I said for the physicists that will bridge this course with the physics 2, the wave, and thermal energy. Same thing with heat. We're not going to deal with heat. A matter transfer, for instance. Electrical transmissions and radiation, electromagnetic radiation. We don't deal with those. That's physics 2. And, of course, that just names a few. I haven't talked about nuclear or chemical explosions, that kind of thing. Is equally as important as work is the ability to do work quickly. Excuse me. If you are in a position, perhaps a director of some project at a company, and they want you to hire workers, whether or not they be computer programmers that know some engineering or mechanical engineers, and sometimes the group will have an electrical engineer depending on what you're building or trying to solve. In fact, a number of maybe even civil engineers. You will find that you want to hire somebody that can do the work more quickly, because usually there is a deadline. And it's hard to predict whether or not someone can do work quickly. Many factors depend on whether or not people, both in wage earners and salary earners, can get some work done. But the way we define how quickly work can be done is called power. Well, we're familiar with powers of machinery. Human power is a human resource situation. We define power in science, excuse me, by the average value of power, which means you might start up slowly, hit an inflection point where you go to a maximum, then toward the end of the day you wind down. So average power would be the power you would perform during the entire interval, although you have change-up. It's defined to be the amount of work you can do in a given period of time, with the understanding that time universally is measured in seconds, which is a very small measurement. Instantaneous power at some point in your performance would be a limiting sum and actually an integral notation, because power is work, integral notation divided by a scalar, which is time. We will not be dealing with the derivative of the work function per time, because they usually are pretty elaborate unless you're talking about a spring, and we don't look at power of a spring, because its net amount of work is 0. If, however, you did look at, excuse me, how work is changing with respect to position, and position, of course, is the second variable of work, displacement. Power then would be a constant force or an average force acting through a first derivative of displacement over time, which is the velocity. So if something is moving and you want to find its power, if you knew the constant force being applied, you can multiply it by the constant velocity, or the velocity that it's moving at that instant in time. All the units there are Newton times a meter divided by a second, which is defined as a watt, named after an American actually, and it has the symbol capital W, which looks like weight. Generally, we do not abbreviate work to W. We just call it, we just spell out the word, even in equations that you use it. Initially, during the Industrial Revolution they had horsepower. 746 watts is equal to 1 horsepower. And notice here I'm using an hour. Your JEA power companies use kilowatt hours, which is really energy, but a kilowatt hour is really power times time and hours, because they're not about to use seconds. So 1 kilowatt hour is equal to 3.6 times 10 to the 6 joules. Kind of an interesting conversion, because we already know, excuse me, light bulbs are in watts, are certified in watts. The last frame talks a little bit about, this completes this lesson before going on to the next lesson, which is some examples of how we do work in conserved and non-conserved systems. The summary of what lesson 6BD is here: work done against a mass's inertia, work done on a mass, work done by resistive forces, work from a force as a function of displacement. That was your spring, and it should not replace the discussion at the end of Chapter 7 and the beginning of Chapter 8. So you still really need to study Chapter 7. It also has, at the beginning of Chapter 7 is a bit of a review of the dot product, which was your quiz today, as a matter of fact. I'm going to go ahead and go to lesson 7A, but I would like to take a break, ladies and gentlemen. There's one I held while you were, okay. I'm going to go ahead and go to lesson 7A, but I'd like to stop for about how about a 10-minute break? I've got to go clear my voice, and I got to replenish my water glass. So let's take about a 10-minute break. Just mark where your clock is, and I'll see you back here in probably less than 10 minutes, but I'll wait 10 minutes for everybody, if you don't mind. Oh. Ladies and gentlemen, it's been about 10 minutes, so let's go ahead and start with, this is one of two more lessons we'll be doing today. Obviously, I generated this one. The introduction of gravitational potential energy, and actually the conservation of mechanical energy, which involves our springs that we were talking about, and friction a little bit, but Chapter 8 kind of brings it all into perspective here. Your text uses the same example I have here, but I talk about it a little bit differently. I say, consider a mass M being held and moving with constant velocity upward. In other words, I've got to hold it, usually on its side, and I'm moving it from, say, a tabletop where the initial velocity was 0, and I'm going to call the tabletop my reference height, which will be h sub I, which equals h sub O, which is going to be defined to be 0. And then I'm going to lift it to a certain height final of h, and the final velocity there would also be the same that I had before. I'm still holding it at that point in time. How much work is done on the mass M? Well, here's a case where the velocity was constant, so the answer would be 0. So the change in kinetic energy is 0. No work was done on the mass, and yet you and I both know I have to hold that mass against its weight in order to get it to the height that we now have it. And there are then two forces acting on the mass between height h sub O and h final. I'm going to go ahead and determine the work done by each of those forces, and if indeed no work is done on the mass, then the sum of those works done by those forces better be 0, as illustrated by our discussion of work. Work done by the force of holding the mass would be the force with which I'm holding it times the cosine of 0 degrees, because I'm holding it with a force up, and it's moving up. And the angle between those directions is 0. So I can evaluate that as 1. So the work that I'm doing, F times H, it's got to be against something other than its mass, and a lot of you can guess what that is immediately. Then the work done by the weight, which is caused by gravity. Gravity acts down, displacement is up, so the mass of this object, which is its weight, times the cosine of 180 degrees is the same change in height. Well, the cosine of 180 degrees is minus. So the work being done by gravity is really negative, and it's minus WH. Well, when I lift it to move it, that force is mg, the weight is mg. Therefore, if I add what I have here for the green amount of work done, and the dark blue, which is the work of just my lifting it, ends up being 0, which kind of validates the fact that the mass was then moving with constant velocity. The work was done by the holding force as well as gravity, so I had to do work up when gravity was doing work down, because the displacement opposes the actual weight of the object down. The last term, mgh, which is the weight times the height, is defined as the gravitational potential energy that the object has with respect to some reference position. In this case, I'll let the reference position be the height of the table. It could be the height of ground level, or the height to the center of the earth. Excuse me. But usually you will set a reference in the laboratory or wherever you're working, the ground, the floor. MGH, or capital U sub G, that should be a sub G there. This is the amount of energy put into this system by your force lifting the mass a distance of h. The system can retrieve this work if the holding force that we were using is removed and gravity is free to accelerate the mass, thus doing work on the mass. Free fall is gravity exchanging gravitational potential energy of position to energy of motion. Kinetic energy versus by way of the conservation of energy principle is what is happening. I also should make a note that the initial and reference position of this mass, when I first lifted it off the top of the table, I could have taken it to the moon, sprang it back, and continued to lift it to its final height. And the discussion of the work being done here would be the same, because it's only the initial location and the final location that determines the displacement of this mass. Here, where it talks about the exchange of kinetic energy to potential, the equation of bottom half of the page is set equal to 0 because whatever gravitational potential energy you gain, once you release the force, you can get that energy back as energy of motion. Free fall is an isolated system. It's the Earth acting on mass. With no energy going into or out of the system, once you release the mass, and it begins to fall in free fall. Similarly, in the case of a spring as an isolated system, once I have compressed it or elongated it, I got out of the system. The change in its kinetic energy of motion plus the change in the spring energy equals 0. So an isolated spring that has been either elongated or compressed is also an isolated system. In other words, mu sub s is the elastic potential energy as opposed to gravitational. The force of gravity and the restoring force of a spring are conserved forces. These forces can do work within the system. Forces that are non-conserved do not put energy into a system, like we are putting gravitational potential energy in the system when we lift the mass. When we compress the spring, we were allowing the spring to store energy in its coils so that it begins to oscillate. Forces such as friction or heat, sound, vibration, or other internal energies such as cracking and sparking and bending and other deformations are non-conservative. Usually the bending and sparking, like auto accidents, never go back to their original fender shape type thing. Ideal spring systems and gravitational systems are conserved energy systems, and we will confine our conserved energy systems to just those two types. And of course, position plays a role. Linear position plays a role in both of those conserved systems. Another way of comparing systems as conserved or non-conserved is by path or displacement taking. Bounding conditions for displacement functions. In other words, from one place to the other, how did you get there? Was it linear? Was it square, x squared, like the spring? Was it like going to the moon and back? That's very elaborate. The amount of energy between the potential and the kinetic is path independent. Whether or not the path is short or long bounding conditions, then the system is conserved. And that's typical of your springs, straight up and down, or right to left in horizontal springs, or the gravitational field, which is all vertical, up and down. If the amount of energy between potential and kinetic is path dependent, in other words, if you push something along a rough surface, you're going to be doing energy against friction. You'll get less energy back out of that system with longer distances. And in fact, it will quit and just sit there. It's not going to go spontaneously back to where it started if you have friction using up the energy of the system. between potential and kinetic and vice versa, the system is then non-conserved. In other words, you cannot get as much kinetic energy out of the system as you put in it, which is potential energy by virtue of position. A qualitative, the sum of all conserved energies plus the sum of all non-conserved energies should be equal to zero as an isolated system. They consider the universe an isolated system. If we study thermodynamics, you'll find the entropy of the universe, though, is not conserved. We appear to be losing energy. We won't go into that. But the equation that I have set up here is the change in kinetic energy plus the change in potential, which could be two expressions. It could be gravitational, or it could be a spring, plus any internal energy. And notice this could represent friction, because it is interacting between two surfaces, would equal to the change in energy of the system, which would be zero if it's isolated. And also another way of looking at this is the amount of energy that you have that's conserved would exactly equal all of the energy not conserved. So the difference in these two expressions would be zero. Here I've put in all 5 possible work considerations for your problem solving, ladies and gentlemen. This really is the general equation you want to use in order to tackle all the problems in Chapter 8. Does it have a change in kinetic energy? And it is on the left-hand side of the equation because it is conserved. Is there an up-down motion, which means there is a change in gravitational potential? Is a spring involved? Is it at an angle, going up an incline? Is it vertical, or is it horizontal? Then the non-conserved works would be friction. And if I apply a force that is out of the system and continue to apply it, not like a spring where I just quit, I compressed it, left it alone. I could also be either pushing, that would increase the normal force, or I could be pulling it, and that decreases the normal force to a point. This would indicate the entire isolated system. Let's consider some examples. In other words, let's do some problem solving now. First of all, case 1, a 4-kilogram mass is pushed a distance of 2 meters across a rough level floor with constant velocity. If the pushing force P is horizontal and equal to 8 newtons, determine the coefficient of friction. The work energy equation is just a repeat of everything I gave you, but the work now is a work of push. And since delta V was equal to 0, delta K is equal to 0. Now that leaves then, out of 5 expressions, it leaves 3. So I ask myself, is there a up-down change in gravitational potential? No. Was there any spring involved? No. This equation then becomes one of the equation then becomes one of nothing in that conserved system is being considered. First of all, the velocity was 0. Remember, the change in velocity was 0. So this equation becomes one of the work against friction plus the work of pushing. Now, this problem could be solved using Newton's second law, but here we're using a work function because if the initial velocity was the same as the final, it could have been moved to the moon and back. We're not interested in what happens in between. Notice that I have the frictional force dotted into a displacement here, plus the push force. Then I have that equal to push force dotted into the change in the displacement x or s equals mu, the coefficient of friction, times the normal force times the cosine of 180 degrees, which is the direction friction will work, times the change in s, plus p, the pushing force is horizontal. So all I have to do is do the cosine of p's direction is the same as delta x, s, and will give me a value of 1. Well, all of these delta S's go out. And when they go out, we find an expression that can be derived by summing forces. So here's where Newton's second law agrees with the conservation of energy principle. Solving these, moving right on, mu then is equal to P divided by mg, and we find the coefficient of kinetic friction is about 0.2. Looks like it might be kind of aluminum and maybe wood or something like that. And of course, if you wanted to draw a free body diagram and apply Newton's second law and solve for mu a little like you did in a problem on the last test, you would probably verify this to at least one significant figure, and I think it's even 2, to be frank with you. Case 2. Again, looking at our work energy theorem equation with all 5 terms, I drop a mass of 5 kilograms from a height of 50 centimeters onto a vertical spring, which is then compressed by 0.2 meters or 20 centimeters before coming to rest momentarily. If you've had anything to do with springs, you realize that's momentarily. Determine the elastic constant of the spring. Now, I look at my work energy equation and I realize that there was implied no friction, and I did not push the spring down. I released the mass, got out of the system. So this is a totally conserved system. Looking at the change in the kinetic energy, and now I have identified the final minus the initial for kinetic energy, the final minus initial of gravitational potential energy, the final minus initial of the spring's conservation of energy, and I went ahead and put the equation in. However, I probably realized that the initial velocity when dropped was 0. The final velocity at the moment of compression is 0, so delta K was 0 all along. So throughout the fall, certainly its velocity increased, and then it decreased. So the net amount of work done on the mass is 0 because its initial velocity was 0, its final velocity was 0. Now, we didn't take it to the moon. All we did was just drop it. Then the final potential energy minus the initial, the final spring energy minus the initial. Let's analyze MGH final. What I've done is I have allowed my reference height to be a height where all of the motion started. Notice I have h sub I listed. I have a diagram with everything that I know about the problem, like the 50 centimeter height above the spring that has not been compressed or elongated, is just sitting there. The coils have to have some separation distance, though. I call that my height as the problem begins, or at time t equals 0. And I want to define it as my 0 position. Then at the bottom, when the spring is momentarily compressed, I call that my final height. And the problem stated that that was a compression of 0.2 meters. The height above the spring was 0.5, so the total distance from the release point of the mass is 0.7 meters. But it is below the rest position, like being below the axes in a work graph, which means it's minus 0.7 meters then. And minuses become extremely important. I know from where the spring was just sitting there waiting to be met by a falling mass, the rest position is identified as y sub o, which equals 0. It's also its initial position. I know then that from that position to its compression, I could label that as 0.2 meters. With that in mind, MGH final then would give me a value of mg times minus 0.7 meters. But my initial height I defined as 0, so I can get rid of one of these remaining 4 terms. I can come over here and look at 1/2 ky final squared. And notice that the spring does not recognize the fact that it was negative because I compressed it 0.2 meters. At its initial position, this arrow that goes to 0, y sub initial is defined to be its rest position and is 0. I have eliminated from my 5 expression work equations all but 2 energy measurements and their interaction. One is vertical, so I think it's gravity. The other is the spring because it was compressed. Well, let's put those equations together then. And notice that I have mg, h final, which was negative, plus 1/2 ky final squared. So the equation becomes, if I move the mgh on the other side of the equation, what the potential energy lost, minus, remember it was minus mgh final, it's going to gain into the spring, assuming ideal conditions. And so moving right along. Given the values, mg, now g here is not negative. It is barely there to convert a mass to weight. We've already looked at the signage. However, it fell 0.7 meters according to my reference height, which was above and called h at time t equals 0, equals 1/2 k, and its compression. Well, obviously, I think we had read that we're trying to find the spring constant. There is a technique like this used in industry in order to measure what a spring constant is. When they're making springs, they will pull off, usually they try to have about 10% that they pull off and test to make sure that the specifications of the springs that they're making, they're not springs for trains or cars in their, of course, springs and cars, for quality control. This is a technique that they use. I don't know if any of you are interested in that. Anybody interested in that? Do I have a yes? Can you hear me, folks? Oh, good.
Yeah, we can hear you.
Oh, thank you. I'm doing all this talking, but my voice is a little better now. All right, here we go. This problem would have been difficult using dynamics because the acceleration during the 70 centimeter fall is changing. The free fall acceleration from a height of 0.5 meters above the spring, of course, is 9.8 meters per second squared, acting down, of course. Once the 5 kilogram mass touches and compresses the spring, it decreases again its velocity to 0. At that point, where the spring mass system momentarily came to rest. So the net amount of work done on the mass here was 0. Notice that we recognize that non-conserved forces were not involved. No push was given to the mass. No initial velocity was given to the mass. It was just dropped like we do in free fall. No frictional interaction or drag. And it was continually transferring potential energy of gravity into kinetic, and then kinetic gravitational into spring energy, and then spring conservative potential energy. Here's a second example. A mass of 3 kilograms, starting from rest, slides down a rough 30-degree incline and encounters a spring whose constant is 600 newtons per meter. And notice that spring constants are rather large. If mu sub k is 0.22, and you can put a 0 on that if you want to, as far as measured in the diagram, how far did the mass slide before the spring mass system momentarily comes to rest? A similar problem, but the spring now is compressed at an angle, and I have friction. So I suspect that out of my 5 expressions for conservation of energy, since I didn't push it, it started from rest, the work of an applied force is 0. The kinetic energy is 0, but I've still got to deal with gravitational and the spring and friction. So I have added friction. as kind of to develop our expertise in using the work energy theorem. In this case, I have let the final height be equal to 0, and that's after the spring has been compressed 20 centimeters. And that 20 centimeters is with respect to the dashed line that I have there on the incline. The vertical displacement is not the 20 centimeters. The vertical displacement relative to gravity is going to be less than that. And notice I have found that value by using the heights of compression over the S value of displacement to get this at the sine of 30 degrees, so that I can actually get then the height, since I know S was 20 centimeters. So my final height by my 0 as reference position becomes 0, but that then makes me lose that initial potential energy that I had, which would be mgh initial up here, and I don't know that value because one of the things I want to determine is S, and so I don't know S. Then the final energy of the spring, because it's compressed, the initial is 0. We know if the spring is just sitting there, it has no potential to begin to oscillate. And of course, friction to the right is non-conserved. This would be friction times delta S, or just S. But I know that friction opposes the motion. It is on the right-hand side of this equation. It is non-conserved, and it will dissipate energy through heat. And so I know the force is anti-parallel to the motion. The motion is down the incline, but friction is up. And so you have the cosine of 180 degrees, making the non-conserved work in the right-hand side a minus the small f times S, and the small f is mu times n, and this is a kinetic friction because motion is occurring. Putting the equations in for H, mgs sine of 30 degrees, that doesn't play a role in the spring. It only recognizes compression along whatever orientation it has. And notice that I have the actual value of the normal force as measured along an inclined plane. Now, this fact comes out of our study in Chapter 5, which is mg times the cosine of 30 degrees times S. So we are mixing a lot of things that we learned previously here. Okay, let's go ahead and just solve this very quickly. The equation tells us that the lost gravitational potential goes into spring energy to compress it and to overcome friction, or its work lost to work done against friction. Notice the signage. I lose gravitational potential energy, and I have to gain it to the compression of the spring and gain it against friction, or it's not going to move. If I were to put this expression for the work done by friction on the right-hand side of this equation, it becomes negative because it's in the proper position for losing energy. Here you want to put it as part of the system, and I have to gain that work done against friction so it will move. And in the case of the spring, it will compress it. Up a little bit. Case 3A. We have a mass of 3 kilograms starting from rest, slides down a rough incline, encounters with it. How far, in other words, S, did the mass slide before the spring mass system momentarily comes to rest? And here's where we solved all of those expressions. This equation here, minus mgs sine of 30 degrees, is the repeated equation I was talking about. And isolating then the terms in S, solving for F, here's the S right in here. I got about 1.32 meters. So that's really a solution to the previous equation for my example of a 3A. The next example is what happens if after it momentarily is compressed, then it will exchange spring energy into trying to seek its rest position, and it will begin to push the block with the assumption that the coefficient of friction is not high enough that it will only go a small distance. Actually, we didn't have but a 3-kilogram mass, so about 6 or 7, 8 pounds, which is about the weight of a gallon of milk, so it wasn't that bad. Notice that in that case, I allowed the gravitational potential energy final to be where I wanted to end up, leaving the initial height, my original height, which is the spring compression of H sub 0. Then notice that the final spring energy has expelled all of its energy to get back to its rest position, and the block is not glued to the spring. So as soon as the spring gets back to its rest position, that dashed line, the spring will, it might vibrate a little bit, but it will come to rest because of the block's inertial, and then the block will continue to move up the incline. But it's still got distance to move under the influence of friction, so the expression for friction and the total distance along which it moved from the time that it was sitting at rest with the spring is now going to be a new S value. Now, the equation we have there tells us that the spring loses its energy to do work against friction and gravity here. Notice the spring loses energy, MGH is positive, and mu in the entire composite system is positive. In the work energy theorem, though, it's going to be on the right-hand side of the equation. It's going to be negative. Here we have solved this, and this is covered up. I think that's 0.59 meters. Yes, because the system is non-conserved, friction is present. The distance back up the incline is less than the distance we found going down. In fact, you may want to verify that. Interesting. Okay. Before leaving this lesson, a discussion about the relationship between conservative force and potential energy is needed. If the only force acting on a system is conserved, then work on an object, remember, is the change of kinetic energy times the closed integral or line integral from some initial to final bounded condition, is the constant force being applied dotted into that separation distance. Or in other words, the change of kinetic energy plus a change in whatever potential energy is present, and this may be two terms. It may be gravity and it may be a spring. Thus, the change in the potential energies, if you want to look at it that way, is going to be equal to substituting for delta K, the integral of that force, or negative of that integral, times force dotted into dr, where r is some linear one direction, easier to picture. If r is multidirectional, ijk, then the derivative becomes a partial derivative for x only, y only, and z only. And ladies and gentlemen, we don't do that. That is a partial ordinary differential equations, and that is neither a co-requisite nor a prerequisite to this course. So when the book talks about that, if you've had differential equations, you can relate to it. But because work is a scalar quantity, you have to deal with the I direction separate from the J, separate from the K. In your quiz today, notice that you did have I values. When you dotted I onto I, the direction dissolved itself, as we did in the discussion during our last class meeting. Systems tend to seek their lowest potential energy position or state of motion, which is the most stable position or its most stable state. Now, how can we picture that? Well, I use the picture of a gymnast. If a horizontal bar gymnast is just hanging by their arms, and they're stable. In fact, if somebody were to displace them slightly to one side, they would vibrate to and fro. And if the rosin on their hands had the minimum amount of friction, finally slowed them down, they would just hang there without moving. What do you think is happening if the gymnast at the top of the crossbar? Very unstable. And she will, if her center of mass is just slightly off to the back, she will fall away from us and start rotating toward us. If her center of mass is slightly toward us, she will begin to rotate to us and then away from us. Using the friction in her contacts with, usually they have some kind of leather and some rosin, if it's too high, then she will not finish her performance. So it has to be very careful, a mixture of stopping and control, and the type of heat generated is dissipated in the, actually they use sometimes leather material. Her position is very unstable if she is doing a handstand on the top. Slightest displacement and it will tend to go to the bottom with some friction in the contacts of the bar. She'll begin to stop and exhibit pendulum motion, actually. And if she presses down, she can come to a full stop. The equations in this lesson are applicable to all the lessons you saw in Lesson 6A and 6B. The quizzes to this lesson involve some problems as the students push pushed anything, and I had a Dodge Power Ram truck, and there used to be a question associated with this particular lesson, but it's been lost, folks, when we moved from Blackboard to Canvas. But it asked about work done by gravity and friction when you're pushing a truck up an inclined plane, and the driver in the truck keeps saying, push harder, because the speedometer keeps reading the same value. If the truck is moving with a velocity that's constant, then the people pushing the truck up the incline are doing no work on the truck. Why? Anybody know why? Because, yeah, if you, let's say you're going to the beach and you got all your drinks in the back and everybody's in the back of the truck, and you guys are in the back of the truck and the ladies are sitting in the truck, and you got to get up this incline before you can get over to the beach. Maybe it's part of the bridge or something, and your truck stops. So all you guys get out of the truck and you start pushing it up the incline. And one of the ladies is in the driver's seat, and she keeps saying, push harder, push harder. The speedometer keeps reading 5 miles an hour, 5 miles an hour. And you guys are just pushing as hard as you can. And the little lady at the driver's seat says, push harder. We're still only going 5 miles an hour, 5 miles an hour. Gentlemen, you know you're doing work. You're not really doing any work on the truck, because its velocity is constant. On what are you doing work then? You're doing work on two things. Yes, friction, absolutely, and of course gravity. That's what you're doing. Now, if you increase the velocity, you're doing work on the truck then. That's F equals ma. So you, which is non-conserved and is on the right-hand side of that equation, along with friction, and only the work done against gravity is on the left-hand side. And we did a sample of that in this lesson. I want to backtrack a little bit and look at the PowerPoint presentation that your text gives you for Chapter 8. I have written to publisher a lot of my ideas, and I believe that they, if any of you have looked at this lesson, ladies and gentlemen, well, should I be very frank with you? I think it's confusing. So I would like to kind of walk us through some of this, because this is what your book has got to teach you, or the method they're approaching, and I think they overdo it. I hope that my examples were a little bit clearer. And in our discussion of the Dodge Power Ram, I hope it became self-evident in a way. So I'm going to go back to Chapter 8, Text, PowerPoint. I know it will take you a few minutes to get there, those of you that are still with me. So I would like to take about another 10-minute break so I can take attendance. And I've already lost a couple of people. This gets a little intense, folks, but I've always said online, this course is challenging online. And one of two very challenging concepts is this conservation of energy systems. And I don't even want to tell you the second one because it's coming up in a month. So let's take another 10-minute break. And you want to get to Chapter 8 PowerPoint. That's the text, Chapter 8. And I'm going to take attendance real quick and come back to mine. Oh, and I shut me off. That's cute. Reconnecting. Cute. Uh, hmm. I'm still live here. Oh, I got somebody back. Let's see who joined us. Okay. Oh, I got a couple of people. Glad you showed up, everybody, but I'm taking attendance. Okay. They don't believe that quizzes in the time frame I use establishes an attendance policy. So we'll work on it a while. Take a break. Remember, we got about 8 minutes left. Okay, ladies and gentlemen, it's been 10 minutes. I had a chance to look at Chapter 15, and the only section you may want to look at with regard to Hooke's Law is Section 1. So concentrate on Chapter 15, Section 1 for that homework problem that I have aside. If you've had some experience with springs in a prior physics class, you may not have to look at it. Just go ahead and work the homework problem, which would be quite enough. It's designed to give you some background. Sirway even confesses that they begin to use springs as if you have prior knowledge. And, of course, that's why I spent a little bit of time talking about spring energy. Now, Chapter 8. Do I still have an audience, ladies and gentlemen? Oh, thank you.
Yes, ma'am.
I had yeah, thank you. I hope all of you have Chapter 8, Conservation of Energy. It looks like someone is cutting with a table saw a block of wood, which obviously is some kind of mechanical energy or work being done on the wood, and of course you're pushing it with constant velocity, watching out that you don't cut yourself. He starts out by just saying non-isolated systems. Energy crosses the boundary of the system during some time interval due to interaction with your environment. For instance, the table saw and the block of wood and the person is pushing it. And he has some examples of what we mean by energy transfer. That's good, that's good. And then energy is always conserved. And remember that when we were working work energy theorem problems, we always kind of put everything on one side, both the conservative and non-conservative. And he has, remember, the change in kinetic energy, the same thing we had to the left of the equation. They have only one change in U. I know that could be either gravitational, or it could also be an additional change in the potential energy of a spring. So it could be 2 in the place of 1. Then the change in energy internal could be friction, but it really should appear on the right-hand side of the equation as a negative value because of the cosine of 180 degrees. And then he has W for physical work of pushing and pulling, which is an applied force. Then he has Q, of course, would be thermal energy, mechanical waves, all the other kind of waves you have, I forgot what his MT is, but on and on and on. Electromagnetic waves, electric transfer or whatever. It says that if only the system's velocity, they say speed, but it's got to be in a direction of some kind, as long as you know where you're at, either initial height or final height. The work energy theorem, if you want to call it work kinetic energy, I don't prefer to use that. Kinetic means motion has to appear. And we've studied someplace where if you only apply enough force to overcome friction, it will, if it's not moving, it's not going to start moving. And notice that had the change in kinetic energy then was equal to the actual work done. That's a highly restricted expression, however. You might want to go through some of these questions because they will answer them for you. If you really want to look at this, here's 2, 3 block of surface. I don't ask questions about whether or not it's internal to the system or external. We've already studied internal forces as push-pull and Newton's third law. So if these diagrams work for you, that would be fine. Usually they're not used. Conceptual example, when using the energy conservation equation, I prefer to call it the work energy theorem. To solve a problem, the following steps should be remembered. And as we were working the last problems of my PowerPoint, did we not identify the system? And I not only had a verbalization, I had a diagram of before and then after, when the spring was not compressed and the mass was above it, either on the incline or vertical to it, So it's two diagrams needed, the initial position and the final position. In fact, we will utilize that when we get into our third test with momentum. Identify the beginning and the end of the time interval of interest. Those are your two diagrams. Identify initial and final configurations of the system, and assign appropriate reference values of potential energy. One of my heights was a reference of 0, and then the other example, the initial height was a reference 0. As long as you maintain the same reference height in any given problem, you can make one of the energy values 0 if you're dealing with gravity. But you could say, at my reference height 0, I'm going to define it as no gravitational potential energy. And if it goes down, I know to put a negative sign with it, or a negative sign will end up in the equation. Write the energy conservation equation, write the work energy theorem equation, eliminating or setting terms equal to 0 that do not apply in the situation, and I've been doing that if you recall. We ended up with 5 terms, and sometime we were left with only 3. One time we were left with 2. Can you see how I was doing this kind of specific situation? We were applying it before we even read what your book was talking about. And your book talks about it before they apply it. Consider any following example. And here they've got change in kinetic energy, change in potential energies of some kind. Work against friction is delta E sub INT. And all these other energies, they should have drawn a line through Q because we don't involve heat.
You are now muted.
Only as it's manifested as work done against friction. So, again, that equation is not viable in our study of physics. Your gasoline-powered lawnmower, the time interval includes the process of filling the tank with gasoline, and that's mechanical energy. That's kind of a joke there, folks. You look at it, once you fill it with gas, you look back, and then you start trying to pull it or turn on the key or whatever you have to do. A cup of tea being warmed, well, here's where you obviously would use Q. That is beyond the scope of our homework and the work they do, as a matter of fact. Then notice that they're talking about that same book being elevated a height and then moving back to a tabletop. That follows a little bit of my discussion as well. Then they talk about mechanical energy should be 0, which means if I take the final and initial values, they should be equated to one another. In other words, the final energy's got to equal the initial energy. And of course, the various equations for the two. And they just barely put together MGH, but I think they realize that you may have already studied that in a prior course. There's an interesting quiz here. You might want to think through it. The answers are correct. Go through those. This one I would like to look at because it relates to one of your test items in the last test. And it says 3 identical balls are thrown from the top of a building, all with the same initial speed. As shown in the figure, the first is thrown horizontally, the second at some angle above the horizontal, and the third at some angle below the horizontal. Neglecting air resistance, rank the speeds of the ball at the same instant each hits the ground. I don't know what you think, ladies and gentlemen, but if you use conservation of energy here, any ball that goes up has got to come back down. They gain and then lose that amount of elevation. Same thing with ball 3, which means literally that everybody's final velocity is the same here. And I mean, if you have a horizontal value and a vertical, they all come out the same. You may want to prove this, go back and maybe use angles like horizontal, throw it out, 0 degrees. Maybe vertical, throw it up, say 30 degrees, and let it fall through the same height. You'll find this to be true. I would not mind if you memorize it and just know that this is true, neglecting, of course, any air resistance or drag or maybe an osprey coming and getting the ball and moving it somewhere else. Obviously, this is an isolated system once it leaves your hand. Okay, very good. Then isolating systems, and we've already talked about non-conserved forces, friction, of course, being the number one. When you push an object from outside of the system, that is also non-conserved. When you're maybe pushing against somebody that's trying to keep the block from moving, their force would be back, yours would be forward. There's an example of a positive and then an example of a negative work being done from outside. Then we talk about a ball in free fall, and notice they have defined the initial height as y equals 0, the final height as being h. Obviously, the potential energy at your defined 0 position is 0. And, of course, then they talk about final kinetic energy just before it hits the ground. Interesting little talk about the position, the kinetic and potential energy, because it's a conserved system. Then they talk about ball and free fall, and this is an extremely interesting equation. We will encounter it in fluid systems that has no laminal flow. It will be all ideal flow, which is called streamline. I particularly want to point out that the final velocity squared is a combination of the change in height. If y's height is 0, then the final velocity is the square root of 2gh. And we want to try to make either the initial or final position 0 anyway. But be careful. If you make h a height 0, then remind yourself that y was negative. So a negative y means the square root of a positive number. Do I have some agreement on that, ladies and gentlemen? You just can't say height here is 0 without saying y then. If it's falling, it's going to go down.
You are now
So I do get the square root of a
muted.
positive number. If you get the square root of a negative number, something's wrong. Do I have a yay or nay on that, somebody?
You are
Yes,
now
ma'am.
unmuted.
Yeah, I think I'm getting
You are now
I'm getting
muted.
the same 2 or 3 voices. If you're on earphones and you have your mute, everybody feel free. I'll give you a little more time to answer. Feel free to go unmute and just say yay, nay, yes, no. It encourages me, especially since I'm having voice problems today, ladies and gentlemen. Okay. And notice that I didn't say, well, I'm just going to quit talking because you can read this stuff. There's a real problem with ways your book has presented things. Now, this is because they expanded the picture, but notice the end product here is that same equation we were after, and they just filled in all the JS direction and whatever. So you'll see it in the book without all of the slurred. The major equation here is if you had an initial velocity, it must be considered in the final. And you know that from finding the final velocity in that test problem on the last test, as a matter of fact. So you've had practice here, but you didn't use energy. You used kinematic equations because that G there is constant. So we were dealing with constant acceleration. This example in your book is fun. It's great. If we had a lot of time, I wouldn't mind talking about it. But ladies and gentlemen, ignore it. And I'll show you why. All of the talk, all of the counterweight, sandbag, all of the equations, la-di-da, whatever. Let's go to this example. Now, this example is a little different than mine, but it is a little like when we had compressed a spring vertically and it came to rest momentarily. And that was the end of my problem. This problem has a pop gun that has been cocked. If any of you have these little dart guns and you cock them, and a sphere placed on top of the spring that is already mechanically compressed. And see some of the variables here. The projectile of mass m rises to a position of y sub c. as in the illustration, above the position at which it leaves the spring. This is not on an incline, so it's all vertical. Consider a firing of the gun for which M equals 35 grams. Y sub A, which is your reference height, is measured from Y sub C, which is the way I took one of my measurements. And, of course, Y sub C is 20 meters then. The difference between Y sub C and the 0.12 meters was that distance that I had given for fall, which they didn't do here. They gave you two values, and one is not 0. It would have been more convenient if we had let Y sub A mean 0 and Y sub C then being, what would be, because, that's almost negligible there. Neglect all resistive forces, determine the spring's constant, which goes back to my illustration using the work energy theorem. And notice that they have used it here and they have no conservative work. The right-hand side here, they don't have to consider it. They already know from the examples that you've done that you want to concentrate on U sub G and U sub S and how they're changing. They threw in the kinetic energy, but you have information that we've studied to the point where if you were working this as a homework problem, you might immediately identify delta K as being 0, so you don't deal with it. And then concentrate on the following two binomials in the expression, and notice that the final energy and the spring is 0, minus the initial, which would be the compression. And so this is a slightly different application of the same vertical fall or projectile of an object to or from a spring. Then they say find the speed of the projectile as it moves through the equilibrium position of the spring. Now, I did not do that, but it would indicate that the sphere has gained kinetic energy before it reached its peak where the kinetic energy and the velocity is 0. This is just equating what the kinetic energy would be at that point, not through the entire height. So this work energy theorem expression would have a non-zero kinetic energy at that location, but it's not at its peak. The equation they derive is viable, but you've got to remember that it's with respect to the rest position. So don't start using this equation for a mass that's been fired vertically, because it may not be the velocity where it leaves the spring or the muzzle of a rifle. So it has limited application. But it's interesting to look at that equation. And it is a non-zero kinetic energy, non-zero velocity. Kinetic friction. And, of course, we talked about friction if something is not moving, or if it's moving, what would constitute no acceleration. In this case, they talk about the work that's done by other forces and the fact that the force may change with position. The R's over these values imply that they are a vector. I don't know why they used R, but it is capital, so it's implied. And here they have other forces, could be a push or a pull, and then they have friction to the right. Well, we kind of bypass that because we realized we had a constant frictional value, and we know the displacement, so we can use just the small f dotted into the displacement. Other forces, this goes down, blah, 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 blah. And then eventually it will say that if I want to find how the velocity is changing in time, and this is an average value, ladies and gentlemen, we have not done a velocity dotted into a velocity. So just to realize that situations involving kinetic friction, if you know something about the motion, and they give you a velocity and time, this is really more like dissipating forces, well, of course, involving kinetic friction. I'm not interested in this page, to be frank with you, because it introduces you to a dot product that is, by definition, going to give you anything a dot product is going to give you a scalar quantity. And notice this last equation is just that. It's 1/2 v squared over dt. So it's a time variable function. And this will lead eventually to a terminal velocity. If you have ever studied the drag force of air on skydivers before the parachute is pulled, before the ripcord is pulled, for the parachute. So that's the justification of this equation discussion. Back down and talks a little bit about the change of kinetic energy equation, which we already derived. We just validated it. And they talk about the change of kinetic energy with respect to any push or pull forces minus, well, if it were a pushback, it'd be a negative W here in the same direction as friction. I prefer using the work energy theorem, which would include all of these works. Okay. Putting that in the work energy equation, we find that internal energy here is defined as, this really is, if it's appearing on the right-hand side of the work energy, should be a negative. But this just means what is the value of the internal energy, which may be creating heat. And notice they put it on the side of conservation, which means the negative sign becomes positive. And then any mechanical work, a push or pull that was done. Not confusing. Here's a question you might want to review. They give you the answer. Try to do it. Then they talk about a block pulled on a rough surface. It has a 6-kilogram block. Well, I did something like this, but I pushed. And notice that my force was not in the direction of motion. I had to use a component. The reason I did that is you already had a discussion of what happens when the force is parallel. We started our talk in Chapter 5 about that. So they're really repeating something here with friction that we already know how to do using free body diagrams and Newton's second law. But it's interesting to go through it again. It's easier because you don't have to use the cosine of the angle to find the force in the direction of motion. So I'll leave this maybe for you to review, but we've already gone through this. Here's one where we are pulling. We have not done one like that. At what angle should the force be applied to achieve the largest possible speed after the block has moved 3 meters to the right? That's an interesting problem, and if you do anything with traffic engineering, you might want to look at a problem like that. But I'll tell you, since you know the limiting speed value and you've had homework questions with respect to what was the maximum force, I believe, and I don't recall anybody getting that problem wrong because you knew to equate that value as a value it would acquire, which means everybody did fine. Everybody that turned in homework did fine. But notice they're using the work energy theorem, and they have taken the cosine of the angle, which is what I did when I was pushing, placing it in an equation for the normal force because friction is involved, so you have to deal with the change in the normal force. Since you're lifting, you know it's going to be less than the weight. And the N equals mg minus F sine of theta indicates that N is less than the weight. Fitting that into the work energy equation in the upper left-hand corner, you'll get the following expressions very much like mine. And instead solving for the cosine, and it's interesting that you will have a tangential effect. You'll have sine over cosine for your mu value. And I wish we were doing a lab on friction because this reinforces the tangent of the angle as it's moving is an indication of its coefficient of friction, providing that's the only thing acting, friction, while it's moving. So interesting. Here's where I want to go. Here's a different type of spring problem, and it's on the horizontal. So if you want to make a note that frame number 46 is a new situation for the evening. It says a block of 1.6 kilograms is attached to a horizontal spring that has a force constant of 1,000 Newton per meter. Notice that the indication for thousands is not being used here. And the reason is the book is international, and some countries do not use any indication that you have the thousandths place. So it is just a universal symbolism. On my test, and I hope that in your homework, unless you write it in scientific notation, 10 to the something power, in this case 1 times 10 to the 3, which is a kilonewton per meter, please put your indication for every thousand. In other words, 1-000 newtons per meter. As shown in the top figure, the spring is compressed 2 centimeters. Now, I wish that they had indicated that the top diagram was the spring at rest. They didn't make that evident, but they said X was equal to 0. So that must tell me that's the rest position in the block. If I were to quit touching the block in the upper right-hand corner, it would stay exactly where it is, because that is the spring at rest. Then the spring is compressed 2 centimeters. Well, that is this X equals minus X max, because it's established the amplitude then on compression. And notice immediately the spring has a force in the opposite direction. That minus Kx, I wish they had labeled the X max as 2 centimeters to be more explicit. Calculate the speed of the block as it passes through the equilibrium position, X equals 0, if the surface is frictionless. First of all, the work energy theorem, as I presented, there were 5 expressions. Which of those 5 expressions am I going to use here? Well, first of all, they say find the speed. So I know that I'm going to have a kinetic energy change. From where I compressed it, the initial velocity is 0. It builds velocity as F sub S begins to act on the block. The spring wants to get back to X equals 0. There is no gravitational. There is potential energy of a spring. So we got 2 terms there. Equals no friction, and I no longer have an external force. So this is going to come down to, I hope, 2 expressions. You can never have a work energy equation theorem use with only one. Would everybody agree with that? Somebody want to say yes? Am I still connected?
You're still connected.
You are now unmuted.
Yes, ma'am.
You are now
Thank
muted.
you. I ought to give you folks some extra points. I appreciate it. Okay. Here we go. They have not given you a diagram of the initial position correctly, but I kind of discussed it, and a final. If you do give an initial, don't place the hand there. Just say that's where the initial position is. I wish they'd put that diagram on this page, but they didn't. And so they took the final kinetic energy it would have in your delta K, the initial it did not have, equals, and notice they said that the spring initially had some energy, but when you place it on the right-hand side of the expression, it became positive, that kind of thing. So they kind of skipped a step here. However, they found that the final velocity, if that's the only works or frictional effects you're having, they have actually developed an equation that will give us some idea about springs from Chapter 15, Section 1. Namely, the final velocity is equal to that displacement times the square root of the elasticity of the spring divided by the mass that was attached to the spring, assuming the spring is ideal. So if you're really kind of interested in that square root of K over M, you might want to seek out a little more discussion out of Chapter 15. We'll get back to it when we do our last chapter, however. And they substitute the values with the units since it's a rather simple equation, and then go on to a block spring system, calculate the speed of the block as it passes through the equilibrium position if a constant frictional force of 4 newtons retard its motion from the moment it is released. The kinetic energy and the energy of the spring, which is internal here, which I take exception to because it does not dissipate. The spring takes care of itself. And then they want to look at the work done by some kind of friction. And they went ahead and solved for that. Notice that they have kind of excluded the work done by the spring to push the force. They should have used a U sub F, take exception to that, and solve the equation for friction involved, and of course substitute some values. This final velocity was less than the other, wasn't it? Let me check. Oh yeah, by about 0.11 meters per second. Okay. What if the frictional force were increased to 10 newtons? What is the block speed? And now it's even the work done by friction. Then I think you can go back and subtract it from it, and it'll even be more. Changes in mechanical energy for non-conserved forces. Well, again, they have put the change in the internal energy on the left-hand side. If I put it on the right-hand side, the cosine of 180 degrees would have made it negative. So I take exception to their notation. Other books will still use the work done by friction, or W sub little f. Here is crate sliding down a ramp. Ladies and gentlemen, I did this, but I put a spring at the bottom. It is interesting discussion. You will find that we go again to their expression of the work energy theorem. I hope you recognize this particular equation as being a friction based. So that's kind of a repeat. Now they put numbers in it. How far does a crate slide on the horizontal floor if it continues to experience a frictional force of 5 newtons? And what happens is the box then would come to rest. So the kinetic energy is 0 from the top of the incline, where it was at rest, that you just kind of released it and let gravity do its work down the incline. Then the friction along the road is the same as it was on the incline, and it came to rest again. And all that happened was the loss in the gravitational potential energy was gained to the work done against friction along the board and on the ground. That became a 2-term expression out of 5 change in values that are in the work energy theorem. Incidentally, this problem can also be done using dynamics and Newton's second law, but you'd have to do it in 2 segments, the inclined plane, and then add whatever final velocity it had at the bottom. Make sure it had a horizontal component because the bottom is at an angle, and then how far it would go before rest again. So the energy problem here has made that problem easier to manage, because remember, we don't care how the object is tilted or whatever. We're looking at the end products based on energy conservation. Okay. Here's where decides that the speed of the crate when it arrives at the bottom of the ramp may be so large that its contents may be damaged. And they talk a little bit about what angle then would you like to move the ramp. There are tables for this kind of stuff, but this is how you develop it. And I take exception to the fact that they did not write the equation that they've been developing. If you want to pursue that, that's fine, but I'm not interested in it. Now, I believe this is the last situation of the afternoon. Don't everybody say hallelujah yet. A block having a mass of 0.8 of a kilogram is given an initial velocity of 1.2 meters per second to the right. And it then collides with a spring whose mass is negligible, ideal spring, and whose force constant is K equals 50 newtons per meter. Well, they failed to tell you that the spring was at rest, but it's kind of obvious from the diagram. So their initial diagram is viable. the mass has not even interacted with the spring yet, so it's really not part of the problem, except to recognize that the only energy coming into that spring system is 1/2 m velocity that it has squared. Assuming the surface to be frictionless, well, we don't assume anything. We let, or call it rough, or call it frictionless to solve the problem. Calculate the maximum compression of the spring after the collision. The assumption there is that it does not bring more kinetic energy into the spring system than the spring can manage. And it looks like they pretty much compressed that spring, so all of the coils are almost touching. And if they touch, internal friction is going to cause that block to stop more than just the elasticity of the spring. So we have to know that when we put energy in our spring systems, that it can manage the compression or the elongation. It's not going to go haywire or start firing off the mass. The third diagram there, C apparently has been compressed less than the total compression capacity. Moving on then, change in kinetic energy in the spring. It had some initial kinetic energy, went all into the final spring energy. The spring was at rest, so it had no initial spring potential energy. So this ends up being also a two expression. Work energy theorem application. Suppose a constant frictional force acts between the blocks. This is interesting to look at. Go back and notice that everything is the same except you bring in on the left-hand side, so it is positive. If I place that mu sub k mg x sub c value, which is the total distance that it moved before the spring compressed itself, managing all the energy. Since it is on the left-hand side, it is positive. So solving that for x sub c, and they have the equation as you see there in a small distance. And of course, now you have three terms. It is my practice when doing work energy theorem to try to confine, after you have evaluated the work energy theorem equation, to have not more than 4. We've done a lot of 2s. We've done some 3s. And your homework will reinforce that number. 2, 3, you got to have 2, 2, 3, or 4. That's the limit in the time frames that we have. If you want more, there are some examples that I did not assign for homework. And it's usually toward the additional problems at the end of the chapter. Feel free to work any of those that you have answers for if you're curious about how to manage 5. Or technically, you could have 10 whole terms. Well, yeah, you could. 1, 2, 3, 4, 5. Oh, even more than that. We don't do that. 2 blocks are connected by a light spring that passes over a frictionless pulley, as you see in the diagram. And as soon as you release mass 2, it is heavy enough to move the spring system horizontally and do work against that mass, and it falls a height h. Now, this problem is interested in how you evaluate it. It looks like it would be a lot of expression, but reading the problem, you start with the masses at rest, and then as you allow that mass hanging to reach its bottommost point and come to rest because of the tension in the string, we have 4 energy terms because friction is now put on the left-hand side of the equation. And notice if it came to rest, we end up with only my classic 3 limit. And again, evaluating the work energy theorem, even if friction was on the right-hand side, it would be minus F sub k because of motion times the height that fell, and then bringing it to the left-hand member of the equation, it becomes positive. And we have generated an equation that if you have a homework problem exactly like this problem, you can with impunity use this equation because we have discussed it. If you're using an equation that has not been discussed in your book, you better justify it because it may be wrong. Okay, next. Some books like to illustrate where the energy went. The gravitational potential energy, because the mass hanging had some. Total energy of the system was that change in height with respect to gravitational potential energy. The spring was not pulled or compressed. Notice that a little bit of internal energy, elastic potential energy being lost as gravitational potential energy is being lost. But if you add up all of these values, which is a little hard to do, they didn't give you enough numbers, it's supposed to be the same total energy. Okay, maybe I can believe them. So you got to explain where all the energy went. Then it also talks about what happens when you still have a little elastic potential energy because of the stretching and the internal energy of the system, and it's at its lowest gravitational potential, which they failed to tell you. So when it falls to a height h, at the bottom of that height h is your reference height where gravitational potential energy was defined to be 0, using the work energy theorem, of course. And of course, there's the diagram. And then power. Power is the time rate of change of energy. The power of an inclined plane, which is a simple machine. They talk about it is a force times a velocity. Again, that equation is more appropriate to the inclined plane, whatever force is acting. And of course, that's a component of its weight down the incline. And then units of power, we sort of discussed that before. And they've actually done a little bit of the conversion of the unit. Then here we go to an elevator problem. Now remember I said elevator problems are really summing tensions and weights, and so I did not have you study that. So if you would like to forego frame 66, although it's not that hard because it's like a hanging mass, frame 66 through, and there's a couple of them here. This is the tension in the cable. If that tension is greater than the mass of the people and the mass or the weight of the elevator and the people in it, any friction between the driving wheels on the side, you're going to go up. And so they talk about power then as being the tension or the results of tension along with the friction times its actual velocity. Most elevators are changing velocity, either increasing or decreasing. So I don't particularly like their presentation. A little unrealistic. What power must the motor deliver at the instant? Well, we go to those equations again and find T, go back to the T equation and V. Again, if it's an elevator, I'm not going to put that on a test. We really need to spend about another hour if we do elevators, even going back to chapter 5. And we just got to move forward, ladies and gentlemen. This is frame 69. Oops, wait a minute. Here we go. And that's the last. So frames 66 through 69 are not content. Nowhere in the state-mandated course description do they mention elevator problems, so the rationale is we don't really need time to pursue that if you don't mind, ladies and gentlemen. Now, I did not go back and use the text PowerPoint, but if you need a discussion of the beginning of Chapter 7 with the dot product, feel free to do so. In fact, I'll probably know after the quiz how well you have looked at the dot product and how you can extract an angle from the dot product. There is another vector product, and it is a product where you cannot extract the angle. So the dot product becomes, with regard to I, or the x direction, and the angle it makes, as you recall from a homework problem you had at the end of Chapter 3, where you found the x, y, and z angle, which is sometimes referred to as alpha, beta, and gamma, as well as the magnitude of the position vector in IJK notation. So we've had some background in that. At this time, I'm going to go back to conference and see if you have any specific questions, and give me a minute to get back there. And I'll have a little bit of time. What time is it? Ooh, okay, well, a little time to answer any questions that you might have with respect to our chapter 7 and 8, ladies and gentlemen. Okay, here we are, and I know I'm live. Any questions, anybody? Now, I've got everybody back that was here initially, so welcome everybody back if you took a break. But there at the end, I was only doing what's in the text and sort of elaborating on some of their omissions. Does anyone, I'm live now with you. Let me just type something in. I'll just say, hi, everybody. How's that? Whoops, wait a minute.
I don't have any further questions.
Pardon?
You are now
Yes, ma'am.
unmuted.
I don't have any further questions.
Okay. Thank you. I tried to have this lesson on a Thursday so that you have 5 days to look at those 5 aspects of the work energy theorem, which other books call delta K plus delta U sub G plus delta U sub S equals the work done actually by friction. So the right-hand side of that equation is negative, and your book keeps putting it on the left-hand side where the conserved forces are. And the book neglects to mention that a non-conserved force is when you're pushing something or when you're pulling something against another force. It is a little weak. But the reason why they do that is they know that when you're dealing with the work of push or pull, that which can cause acceleration usually will cause, excuse me, usually will cause, excuse me, got it, usually will cause a constant acceleration. So you will go then to Newton's second law to work that problem. But if the acceleration and the force you're pushing it changes, you have to go to integral notation of work, and it comes back to the work energy theorem, ladies and gentlemen. But I think you'll find in your homework that mostly it's just friction you're dealing with, not an applied force. So I would recommend, how many of you remember that you have at least some examples where some kind of push or pull are done on a block? Did everybody recognize that I had an example of push? The book had an example of pull. You may want to study those a little more closely. As simple as they appear to be, they are, because you can use the free body diagram and Newton's second law to also do those problems. On the next test, if that's the only forces that act, you don't even have to use the conservation of work energy theorem to do the problem. You can recognize it is constant acceleration and use a free body diagram, and please use one, and use the sum of forces equals the sum of masses times the acceleration of the system. I'm going to word the problems on the next test, though, to call for energy, not forces. So be careful. Try to ask yourself, will the acceleration be constant? And if you can't answer that, you better use conservation of the work energy theorem. Does that help kind of delineate where the techniques of this week's lessons are not the same as Newton's second law? Well, everybody stayed with me. I appreciate that, because I'm trying to give you some clues how to manage things. If there are not any other questions, ladies and gentlemen, I wouldn't mind dismissing you. If somebody has a question that everybody needs to know, I'll try to tell you at the beginning of our lesson on Tuesday.
Have a good weekend.
Oh, absolutely. All of you, those of you that are on earphones, I like the fact that you're using them because you don't hear all the distractions. And if I am too loud, if you'll kind of tell me, I know you can tone those down. And although I had a little voice problem, I think I'm still good for tonight's talk. We're doing circuitry tonight, folks. Resistors and capacitors. Wish me luck. One of my favorite topics, although I like the work energy theorem, as you probably found out today. Goodbye, everybody. Have a lovely weekend.
Unmuted. You are now muted.
Thank you, John. Thank you, Ainsley. Yes, very good.